AI hallucination does not mean the model is dreaming. It means the answer sounds confident, but the facts are not grounded. A language model predicts the next token from patterns in the context. When the context has solid evidence, the answer can stay anchored. But if key facts are missing, the model still has to continue. So it fills the gap with likely words. The sentence becomes smooth, but one detail may be invented. That is hallucination, fluent prediction without a reliable source. It gets worse when the question is vague, when the topic is obscure, or when you ask for a source the model has not actually seen. RAG and tools reduce hallucinations by bringing fresh evidence into the context, but they do not remove the risk. The model can still misread, overstate, or combine facts the wrong way. Simple idea. Do not only ask, does this sound right? Ask, what is this grounded on? Coming next, inference cost and GPUs, why AI answers are not free. Every time you ask AI a question, a meter starts running. Not money first. Compute. Inference is the moment a trained model is being used. The model takes your prompt, reads the tokens, and predicts the next token. Then it predicts the next one, and the next one. Each new token is not a simple lookup. It is a huge stack of math across billions of weights. GPUs make this possible because they can do many small calculations at the same time. Think of a GPU like thousands of lanes working in parallel. But parallel does not mean free. A longer prompt means more tokens to read. A longer answer means more tokens to generate. A bigger model means more weights to move through. More users means the same GPU has to share the work. That is inference cost, the compute, memory, and electricity spent while the model is answering. This is why AI apps charge per token, slow down when demand is high, or use smaller models for simple tasks. Training is the expensive work that creates the model. Inference is the repeated cost every time someone uses it. Simple idea. Every AI answer is generated token by token, and each token spends GPU time. Coming next, temperature and sampling, why the same prompt can produce different answers. Ask the same AI prompt twice, and the answer may change. Temperature and sampling are the reason. The model does not choose from every possible word equally. For the next token, it builds a probability list. Some tokens are very likely. Some are possible, but weaker. Some are almost out. If the sentence is, the sky is, the list might put blue near the top. It might also keep clear, dark, or gray lower down. Sampling means the model picks one token from this list. It can pick the top token or a less likely one. Temperature changes the shape of the list. Low temperature squeezes probability toward the safest option. Same prompt, similar answer. High temperature spreads probability out. Now the model can choose more surprising tokens. That can sound creative, but it can also become more random. Temperature does not add knowledge. It only changes how risky the next token choice is. A common mistake is thinking, temperature is an intelligence dial. It is not. It is more like a randomness knob after the model has scored the options. For factual work, use lower temperature. For brainstorming, raise it carefully. Simple idea. The model scores possible next tokens. Sampling chooses one. Temperature controls how adventurous that choice is. Coming next, agents and tool use, how AI stops just answering and starts taking actions. Most people think an AI agent is just a chatbot with a fancier name. But an agent is different. It can take a goal, plan steps, use tools, read the results, and decide what to do next. Imagine asking, compare these two flights and book the cheaper one. A normal model can write advice. An agent can open a browser, search flights, check prices, call an API, and come back with an answer. The core loop is simple: goal, plan, tool call, observation, next step. The model chooses the next action. The tool does the outside world work. The observation tells the model what happened. Tools can be search, code, files, a calendar, email, or a database. The agent does not magically know everything. It gets permission to use specific tools. That is why agents feel more powerful. They turn language into actions. But that is also why they need limits. Bad tools, bad instructions, or too much autonomy can cause mistakes. Simple idea. A chatbot answers. An agent acts, checks, and continues. Coming next, MCP, the standard way agents connect to tools. Imagine every AI app having a different charger. One connector for your calendar, another for your files, another for your database. That is what AI tools felt like before MCP. MCP means Model Context Protocol. It is a standard way for an AI assistant to connect to outside tools and data. Think of the model as the brain. By itself, it can read the conversation and predict words, but it cannot automatically know what is inside your private apps. And it cannot safely take actions unless something exposes those actions. MCP adds a middle layer. On one side is the AI app, on the other side are MCP servers. A server can say, here are the tools I offer, search these docs, read this table, create this ticket, check this calendar. The assistant does not need a custom integration for every single app. It can speak one protocol, then discover what each server can do. That is why people compare MCP to USB-C for AI. Not because it makes the model smarter by itself, because it gives the model a common port for context and actions. A normal chatbot only answers from what it sees in the chat. An MCP connected assistant can ask a connected tool for the missing context, then use the result before answering. But MCP is not permission to do everything. Good systems still need approval, scopes, logs, and clear user control. Simple idea. MCP is a standard plug that lets AI assistants connect to tools and private data without rebuilding every connection from scratch. Coming next, reasoning models. Why some AI systems pause to think before they answer. Most AI answers like this: question in, answer out. But some questions need a slower path. A reasoning model is an AI model that spends extra compute before answering. It breaks the problem into smaller steps, tests possible paths, and checks whether the answer still makes sense. Think of it like solving a maze. A normal model may choose the most likely next turn. A reasoning model traces a few routes first. Dead end, backup, contradiction, try another path. Only then does it give the final answer. That is why reasoning models are better at math, code, planning, and multi-step instructions. They are not smarter in every situation. They are using more thinking time on problems where steps matter. The trade-off is cost. More internal steps mean more tokens, more compute, and usually a slower response. And reasoning is not a truth guarantee. A model can still start from bad information, miss a clue, or confidently check the wrong path. Simple idea. A reasoning model pays extra compute to plan, test, and verify before it answers. Coming next, chain of thought. What it means when an AI shows its work. People say, make the AI show its work. That idea is called chain of thought. A chain of thought is a reasoning trail. Instead of jumping straight from question to answer, the model writes or uses small intermediate steps. For example, first list the facts, then choose a plan, then do the calculation, then check if the answer matches the question. Each step becomes context for the next step. That is why it can help with math, code, logic puzzles, and planning. But here is the important part. A chain of thought is not a truth machine. If the first step is wrong, the whole chain can sound careful and still be wrong. And many modern AI systems do not show the full private reasoning. They may use an internal scratch pad, then show you a shorter explanation or summary. So when you ask for reasoning, you are really asking for two things. Think step by step and explain the final path clearly. Simple idea. Chain of thought is a scratch pad for multi-step reasoning. Useful for hard problems, but it still needs checking. Coming next, multi-agent systems, when more than one AI worker shares the same task. Imagine an AI that can explain your calendar but cannot open your calendar. That is the gap function calling solves. A function is a tool the model is allowed to ask for. Search the web, read a file, send an email, create a ticket, check a database. The model does not press buttons directly. It writes a structured request. Use this tool with these inputs for this reason. Then the app around the model checks the request. If it is allowed, the app runs the tool. The tool returns a result, and the result goes back into the model's context. Now the model can answer using something real, not just what it remembered from training. That is the important difference. Without function calling, the model can only talk about actions. With function calling, it can request actions. A weather question can call a weather tool. A support question can look up the order. A coding agent can run tests, then read the error, then fix the file. But the model is not the same as the tool. The model decides what to ask for. The app decides what is allowed. The tool does the actual work. Good systems keep boundaries. They show the tool name, they show the inputs, they ask for approval when the action matters, and they keep a log of what happened. Simple idea? Function calling is how an AI moves from saying answers to asking approved tools for real work. Coming next, multi-agent systems, when more than one AI agent works on the same task. And automation follows a recipe. If this happens, do that. The steps are fixed before it starts. An AI agent is different. It has a goal, checks the situation, chooses a tool, looks at the result, then decides the next step. That loop is the key. Plan, act, observe, adjust. If the page changes, the agent can change its route. If a tool fails, it can try another path. But that flexibility has a cost. Agents are slower, more expensive, and need guardrails because they are making decisions, not just running a script. So use automation for stable, repeatable tasks. Use an agent when the path is uncertain and the system needs to reason through the next move. Simple idea. Automation executes a workflow. An agent navigates toward a goal. Coming next, reasoning models. Why some AI answers take time to think. Most AI answers feel instant because the model keeps choosing the next token and moves forward. A reasoning model does something slower. Before the final answer, it spends extra compute trying possible steps. It can make a plan, test a path, notice a contradiction, and change direction. Think of a normal model like answering from instinct. A reasoning model is more like solving on scratch paper before speaking. That is why these models are useful for math, code, planning, and multi-step problems. But the thinking time is not free. More steps mean more compute, more delay, and higher cost. And reasoning does not guarantee truth. If information is missing or the instructions are bad, it can still take the wrong path. Simple idea. A reasoning model spends extra compute to work through a problem before answering. Coming next, chain of thought. What show your work really means. Sometimes people ask an AI to show its thinking, but the final answer is not the whole process. Chain of thought means the intermediate reasoning steps a model uses before it answers. Imagine solving 47 times 18. You might write scratch notes, split 18 into 10 and 8, multiply both parts, then add the results. Those notes are your chain of thought. For AI, it is the same idea, a working path through the problem. The model may list facts, test a possible answer, notice a contradiction, and try another route. That can help with math, code, planning, and multi-step instructions. But there are two important warnings. First, a chain of thought can sound logical and still be wrong. Second, many AI apps do not show the raw scratchpad. They may show a short explanation instead. Why? Because raw reasoning can contain mistakes, unsafe details, or irrelevant detours. What matters is whether the answer is correct, grounded, and checked. Simple idea, chain of thought is the step-by-step reasoning path behind an answer, useful internally, but not proof by itself. Coming next, AI Evals. How we test whether a model is actually getting better. Most people imagine one AI agent doing everything alone, but real systems often work more like a team. A multi-agent system is a group of AI agents working toward the same goal. Each agent has a role. One may plan the steps. One may search for information. One may write code. One may check the result. The point is not that each agent is a different person. The point is that the work is split into smaller jobs. The agents pass messages to each other, they share observations, and a manager or router decides who should act next. This can help when a task has many parts, because each agent can specialize. But adding more agents does not automatically make the system smarter. If the roles are unclear, agents can repeat work, argue with each other, or confidently spread the same mistake. Good multi-agent systems need three things: clear roles, shared context, and a stop rule. Simple idea, one agent is a worker, a multi-agent system is a coordinated team. Coming next, agentic workflows, how agents move through real tasks. Part 28 showed multiple agents can work as a team, but a team still needs coordination. Agent orchestration is the control layer that decides which agent acts, in what order, and what information gets passed along. Imagine a task. Research a topic, write a draft, check the answer. The orchestrator does not do every job itself. It sends the right job to the right agent. First, the planner breaks the goal into steps. Then the researcher gathers facts. Then the builder creates the output. Then the checker reviews it. Between each step, orchestration carries shared context, the goal, the latest result, errors, and decisions. If something fails, it routes the work back. If the answer is ready, it merges the pieces into one final result. Good orchestration prevents agents from talking over each other, repeating work, or losing the goal. Simple idea. Multi-agent systems are the team. Agent orchestration is the coordination that turns that team into one task flow. Coming next, agentic workflows, the loop that carries a goal all the way to a finished task. An AI agent is not just one answer, it is a loop. An agentic workflow is the path that loop follows from a goal to a finished result. First, the user gives a goal. Then the system makes a plan. The agent chooses one next action, calls an approved tool, reads what came back, and updates the plan. If the result is good, it moves forward. If the tool fails, it tries another step. If the task is finished, it stops. That is why agentic apps feel different from chatbots. A chatbot gives a response. An agentic workflow keeps checking the world and deciding the next move. But the workflow still needs boundaries. It needs permissions, checkpoints, and a stop condition. Otherwise, the loop can waste time or repeat the wrong action. Simple idea. An agentic workflow is goal, plan, act, observe, and adjust. Repeat it until the task is done. Coming next, guardrails. How agents stay useful without getting out of control. Imagine an AI agent that can send emails, browse files, and book meetings. That sounds useful. It also needs limits. A guardrail is a rule that keeps an AI system inside an allowed path. Not a vague reminder. A real boundary the app can check. For agents, guardrails usually answer 4 questions. What tools can it use? What data can it see? How much can it spend? And when must it stop and ask a human? Picture the agent as a car on a road. The road is the task. The guardrails are permissions, budgets, scopes, and checkpoints. If it searches the web, that may be allowed. If it tries to send money, delete files, or message a customer, the guardrail can block it or ask for approval. The model may suggest the action, but the system decides whether the action is allowed. That difference matters. Without guardrails, an agent can loop, leak private data, or take the wrong action with confidence. With guardrails, it can still work independently, but only inside a safe operating area. Good guardrails are specific. Allowed tool names, approved folders, spending limits, output checks, and logs of what happened. Simple idea, guardrails do not make an AI agent smart. They make its actions controlled. Coming next, Evals. How teams test whether an AI system actually works. An AI eval is not a vibe check. It is a test set for an AI system. Instead of asking, does this feel good? Teams write examples, the input, the expected behavior, and the rule for scoring the answer. For a support agent, an eval might say, customer asks for a refund, check the policy, ask for missing details, and do not invent an answer. Then the team runs the AI on many cases. Easy cases, hard cases, edge cases, tool failures, and unsafe requests. That matters because demos can lie. A model can look smart on one prompt and still fail when the wording changes. A good eval gives a scorecard. Correct, missing, unsafe, too slow, or needs human review. When the prompt changes, when the model changes, or when a tool changes, the team runs the eval again. If the score drops, they stop and fix the system before shipping. Simple idea. Eval's turn seems good into past these tests. They are how teams check whether an AI system actually works. Coming next, benchmarks. Why one public score can be misleading.